Welcome to the Physics 121 pre-lecture video number 9 on vectors, the mathematics of vectors, components, and so forth. So what do we mean by a vector? It's important that we identify and distinguish vectors from other things. Vector has two quantities, a magnitude and a direction. If it doesn't have both a magnitude and a direction, it's not a vector. So graphically, we represent a vector as an arrow, and we have a symbol for a vector, the letter A, with a little arrow hat on top, which is telling us this is a vector. With the arrow hat on top of the symbol, we know that it's a vector and not a number. Vectors and numbers are not the same. So a vector in particular has some magnitude corresponding to the length of that vector, which we could measure graphically. And the direction corresponds to which way it points. So if we define a particular direction as a zero heading, then the angle theta corresponds to the direction. So the length and the direction are both important components of a vector. So for example, if we talk about something like the normal force, that's a vector. If we write the vector symbol n with an arrow on top of it, we can say that is a vector. It has both, implicitly, both magnitude and direction. So in particular, we could, if you imagine saying 4 newtons was the norm, 4 newtons is not a vector. 4 newtons is just a magnitude. Likewise, the weight force. The weight force is not equal to mg. Mg are two numbers that we multiply together, which are not a vector when you just multiply two numbers. Two numbers together is a number. So we want to distinguish between vectors and numbers, and that's why that little arrow sign on top is so important. If I'm talking about the vector, that vector symbol has to be there. The arrows mean this is a vector. Without the arrows there, there's not a vector. You can't put a vector symbol on a number and vice versa. So talking about magnitude and direction. So often we can say, oh, the magnitude, well, that could correspond to some particular quantity. So when we say 4 newtons, that's the magnitude, the length of the vector. And likewise, if we say mg, that corresponds to the magnitude of the weight. Mg is not the vector weight, it's the magnitude of the weight. So if I indicate the magnitude, I write down the letter without the vector symbol on top. So let's remind ourselves a little bit about the mathematics of vectors. In particular, we'll start with the concept of vector addition, which hopefully you've seen before. At least graphically, we have this tail-to-head method. So anytime I have two vectors, so for example, there's a vector A, it kind of points off like that with a particular length there, and then another vector B, which kind of points a slightly different angle, slightly different length, B. I can talk about adding them up. A plus B is equal to some other vector C, and I want to define what C really is. So I'm going to put the vector A down, and we're always free to pick up and move vectors. That doesn't change them. The position of the vector doesn't matter. So that vector there, that's C. If I tail to head, A head, B tail to head, and the two together is C. So A plus B is equal to C. You take the tail of vector B and put it on the head of vector A. Of course, you can do this in reverse. There's B and there's A. You have to draw them parallel. I didn't quite get that, but there's more parallel there. And then again, vector C is going from the start to the end like that. There's your vector C. And they're both the same, whether I do it one way or the other. In other words, A plus B is the same thing as B plus A. Doesn't matter which order you add the vectors in, you'll get the same result. Another important concept we have to be aware of is the multiplication of a vector by a number. So if I have a vector and I multiply it by a number, what does that mean? Well, that means that I take say I have a number n and I multiply it by a vector A, then this is a vector that points in the same direction as A, or rather it points in the same direction if A is positive, and it points in the opposite direction if n is negative. So in other words, multiplying a vector by a negative number changes its direction, and the magnitude of this vector is equal to the magnitude of the number times the magnitude of A. So in other words, if I multiply a vector by 3, I get a new vector that is 3 times as long, pointing in the same direction. If I multiply a vector by -1, I get a new vector that has the same direction, points in the opposite direction. So now we want to deal with vector components again. We looked at this before, but let's have a good look at, make sure we really understand how to contend with vector components. So I have some vector A, and of course the vector doesn't have a coordinate system implicit, but I can always put a coordinate system around any vector that I want. I'm always free to do that. And once I do that, I've got a vector direction theta. Here I'm going to do, the magnitude is going to be A, and the direction is theta. This is in 2 dimensions, for a 2-dimensional vector. And of course, once I have a vector, then I can talk about, so just to emphasize, the numbers A and theta are not vectors, they're 2 numbers. So in other words, I represent the vector as 2 numbers, A and theta. A and theta tell me the length and the direction. That's everything I need to know. What about components? Well, I could have a component in the x direction, A sub x, and a component in the y direction, A sub y. These are Cartesian components because they're lined up with x and y. So I can say A plus AX plus AY is equal to A. In other words, this is a vector equation. I can add 2 vectors to get a new vector where each vector corresponds to a component. Each vector AX and AY with a vector symbol are vectors, but of course I can talk about the magnitudes of those vectors. The magnitude of AX, we'll call that the x component, and the magnitude of AY correspond to the y component. And again, these are numbers. These are 2 numbers, A sub x and A sub y, corresponding to the magnitudes of the vector components. So to define a vector, I can either write down 2 numbers corresponding to the amplitude and the direction, A and theta, or I can write down 2 numbers corresponding to the components, A sub x and A sub y. Either way, I need 2 numbers to define a vector. Once I have those 2 numbers, I can tell you everything about that vector. I can figure out what its length is, what direction it is. I can go back and forth between these 2 numbers. So how do we go back and forth between A and theta and the components AX and AY? Well, this is really just trigonometry. So if let's draw our vectors again. There's our vector A with its length A and its direction theta. And of course, this vector has 2 components, A sub x and A sub y. Those are vector components with magnitudes A sub x and A sub y without the vector signs. So I've got a triangle here. So given A sub x and A sub y corresponding to the lengths of the 2 sides of those triangles at a right angle, I can just use Pythagorean theorem to write down the magnitude of the length of the vector A. A is equal to the square root of ax squared plus ay squared. Again, no vector symbols. These are all numbers here. And likewise, to get theta, I just use trigonometry. I just take the arctangent of ay over a sub x, the opposite over the adjacent, and that gives me the tangent theta. So I take the arctangent. Likewise, if I want to find the components given a and theta, a sub x, well, trigonometry says that's just the length a cosine theta, and a sub y is equal to the length ay sine theta. So I'm free to go back and forth between these 2 different representations of a vector. Anytime I have a vector, I need 2 numbers, either the magnitude and the direction, or the component a sub x and a sub y. I can convert one to the other using trigonometry, but one quantity alone is not enough to define a vector. I always need 2 quantities, 2 numbers to define a vector.